Okay, then let me remind you of the definition of a Cauchy sequence we have defined at the end of the last class period. Yeah, the definition of the Cauchy sequence was the following. We first of all have a metric space with metric D on the subset on the set X. Then we say that a sequence X of n in X is Cauchy if no matter what positive number epsilon we choose, depending on that there is some cutting line n over epsilon, natural number depending on epsilon, such that if two indexes m and n are more than that cutting line, then the difference between the corresponding terms, the distance between D metric, distance between the corresponding terms is less than the positive number epsilon we have chosen originally. Yeah, that's the formal definition of a Cauchy sequence in the general metric space. So if we replace X by the whole real number line R and then replace the D metric by absolute value thing, then what? This definition is exactly reduced to the definition of the Cauchy sequence on the real number line sequence we have studied in the real analysis last year. Then we start with a lemma. What is the relation between the convergence and Cauchiness? Yeah, they were equivalent on the real number line sequence, right? But that's not true in the general metric space here. Yeah, that's our main point for the class today. Well, convergence implies Cauchiness, that's true. But Cauchiness may not imply convergence. So the first lemma over here is that what? Convergence implies Cauchiness if the sequence X of n converges in the metric space to some point X in the metric space, then the sequence is Cauchy. So that means convergence implies Cauchiness. Convergence implies Cauchiness. So its justification is quite easy. Yeah, we do exactly the same proofs as we did in real analysis for real sequence. So suppose the sequence X of n converges to some number X in the metric space X. Then how do we prove its Cauchiness? To prove its Cauchiness, let's let epsilon be an arbitrary positive number, and then from this convergence, there is some cutting line, okay, depending on epsilon, such that if our index n is more than that cutting line, then the corresponding terms of the sequence is inside the epsilon neighborhood around the X. So D distance, D metric distance between the corresponding terms of the sequence X of n and X must be less than epsilon for large enough index n. For large enough index n. So Excuse me. So, what happens if we take two indexes m and n, both of which are more than that cutting line we set up there? Then what happens to the distance between those corresponding terms x of m and x of n? I believe it's time to use the triangle inequality for that metric, right? Yeah, if we take both indexes m and n, both of which are more than that cutting line we did set up at the previously, then the distance between the corresponding terms of the sequence x of m and x of n must be less than or equal to, by the triangle inequality, that's less than or equal to the distance between x of m and x plus distance between x and x of n, right? So we want that to be less than epsilon, which means we want each of them to be less than half of epsilon. So for that purpose, let's change half of epsilon instead of epsilon on the previous line, right? So our cutting line must be n over half of epsilon, n over half of epsilon in the previous line, right? So if both indexes m and n are more than the cutting line n over half of epsilon, then what happens to the distance between the corresponding terms of the sequence x of n and x of n? By the triangle inequality, this step is by the triangle inequality. Triangle inequality. Yeah, that's less than or equal to the sum of those two distances, but both distances are less than half of epsilon from the previous line because both indexes m and n are more than the cutting line we have set up on the previous line. So both distances here and there must be less than half of epsilon, so the whole thing must be less than epsilon. So no matter what epsilon positive number we have chosen, depending on that, there is that cutting line such that if two indexes m and n are more than that cutting line we have set up, then what? The distance between the corresponding terms of the sequence is less than epsilon. That was what we have claimed. So we must conclude what? We must conclude the convergent sequence x of n must be Cauchy. Excuse me. And that's what we must conclude. So every convergent sequence is a Cauchy sequence. That's the first lemma here. What is the second lemma then? As I have already mentioned, Cauchy sequence may not imply convergence, right? So then, what additional condition do we need to add for the convergence of a Cauchy sequence? That's what we are interested in on the second lemma. We have a Cauchy sequence which may not converge, right? Then what additional condition do we need for the convergence of the Cauchy sequence we must add? So let's let x of n be a Cauchy sequence. Which may or may not converge. But for its convergence, we want to conclude what additional condition do we need here? If there is a convergent subsequence of that, that's the additional condition we must add for the to guarantee the convergence of our original Cauchy sequence at the end. If there is a subsequence x of nk, where k is from 1 to infinity, of the original sequence x of n, such that the subsequence x of nk converges to some number x on the metric space X, then we guarantee the convergence of that Cauchy sequence to the same thing. Yeah, that's the second lemma. Yeah, the quotient may not imply convergence. But if we have this additional condition, we add, then what? We guarantee the convergence of that Cauchy sequence. What is the additional condition? The existence of a convergent subsequence of that Cauchy sequence. If there is a subsequence converging to some number x, that's not a number. I will take it back because that's a general metric space. So if there is a subsequence, convergent subsequence converging to something in the metric space, then the Cauchy sequence converges. Let me just write down the sketch of its proof, right? Yeah. So let's let epsilon be an arbitrary positive number at the beginning. And then to look at the convergence of x of n to x, right? So we look at the d distance between x of n and x. And then let's apply the triangle inequality to this, right? By the triangle inequality, the distance between x of n and x is less than or equal to what? Sum of distance between x of n and x of nk, and distance between x of nk and x, right? Yeah, because x of n is a Cauchy sequence, right? For large enough indexes n and nk, right? Then must be less than half of epsilon. Because the original sequence x of n is Cauchy. So for large enough index numbers n and nk, right? The distance between those two terms must be less than half of epsilon plus, because the subsequence x of nk converges to x. Again, for large enough index n sub k, the second distance must be less than half of epsilon as well. So if our index n is large enough, and then what happens to the distance between x of n and x, then must be what? Less than epsilon. I skipped some process, but that's a rough sketch for the proof of it. So we have used what? Quotient of our original sequence and convergence of the subsequence. Yeah. So we will conclude what? The convergence of x of n to x. That's the rough sketch of its proof. Yeah. Any questions or any comments on this? I don't believe there is much difference on the real sequence we have studied in the last year, right? So if you use absolute metric on the whole real number line R, then what? Everything here is exactly reduced to everything we have studied in real sequence last year, real analysis. So the next step is to give a special name to the metric space where every Cauchy sequence converges then. That's our next step, right? On some metric space, every Cauchy sequence may converge. Well, on some other metric space, some Cauchy sequence may not converge. So on the next step, we give some special name to a metric space where every Cauchy sequence converges. Complete metric space. Complete metric space. That's what we want to define on the next step. a metric space X with D metric is complete if every Cauchy sequence in the metric space X converges. Okay, every Cauchy sequence in the metric space X converges to a point X in the metric space itself. So that is the definition of completeness of a metric space. Okay? The first lemma says convergence implies Cauchiness, but unfortunately Cauchiness may not imply convergence in general. So we give some special name to the metric space where every Cauchy sequence converges. Yeah, that's, if every Cauchy sequence in the metric space X converges to something on the metric space itself, then we say that the metric space is a complete metric space, complete metric space. Yeah. Then you already know a nice example of a complete metric space. The whole real number line with absolute metric is a nice example of a complete metric space, right? So because on the whole real number line with absolute metric, Cauchiness and convergence are equivalent to each other. So for example, the whole real number line R with absolute metric is a complete metric space. For sure. Then secondly, what is a nice example of incomplete metric space you may have in your mind? So a metric space is incomplete, which means not complete, which means what? There is some Cauchy sequence which doesn't converge, right? Then what is a good example for an incomplete metric space? Well, let's let L squared, which is a set of all real variable to real valued function, which is square integrable. Yeah, L2. I will call that L2. L2 is the collection of all real valued, real variable functions, which is what? Square integrable, which means the improper integration of square of f on the whole real number line is finite, some finite number. That means, then if that's happened, then we say that the function f is what? Square integrable. On L2, what is the D metric? Let's let D distance between the two functions f and g be what? Be integration from negative infinity to infinity, square of their difference. So on the set X, which is L2, we define the D metric on it. We take two functions f and g in the set X, which is L2, and then this is how we define between their distance. Distance between the two functions f and g is defined by integration of the square of their difference. Then the set L2 with this D function is a metric space. Which we will study more afterwards. So what I mean is, yeah, this D definition, okay, this D definition satisfies three different conditions to be a metric space, right? That's what I mean. So then we will study more about its justification afterwards, not now. It takes much time, so then we will delay its justification to some other time, okay, later. So let's assume, assume we know that that's a metric space here, okay? We want to have some subspace metric of this. We want to have some subspace metric of this. Let's let L sub C square, that's another set, which will be a subset of L square, L2, which is a collection of all real valued, real variable functions such that the function f must be continuous. That's what that sub C notation stands for. That's what the sub C notation here stands for. The function f must be continuous and square integrable. Then you easily recognize this L sub C2 is a subset of just L2, right? Because we did put more condition about continuity. So L2 is just a collection of all square integrable functions. But L sub C2 is the collection of all what? Continuous and square integrable functions. So because we did put more conditions about continuity here, right? So what? L sub C2 is a subset, a part of just L2 there, right? So let's use exactly the same metric D we have used in L2 on L sub C2 as well, right? So let's let distance D between F and G be exactly the same thing. The improper integration on its domain square of their difference. Then what happens? This subset LC2 with that same D metric, that is a subspace metric space of L2. Subspace metric space. Subspace metric on the original metric space L2 with D metric. Right? So what I mean is the following. Here is the original L2 with D metric on, right? That's the original metric space, L2 metric space we have with D metric defined there. And we have some subspace metric, which is what? L sub C2 with the same metric D we have defined. And then this L sub C2 with metric D is a subspace metric of what? Original metric space L2 with metric D there. So we have a subspace metric of the original metric space. That's what it is. Then we want to claim that this subspace metric is not a complete metric space. That's what we want to claim. Actually, the original larger L2 space is a complete metric space, but its subspace here, L sub C2, is not a complete metric space. That's what we want to claim. So that will be an example of, this will be an example of what? Incomplete metric space, incomplete metric space. That's what we want to claim. So we want to claim that the subspace metric there, which is L sub C2 with D metric we have defined, is not complete. That's not a complete metric space. Yeah, that's what we want to claim. For it to claim, we have to figure out a Cauchy sequence which doesn't converge, right? We want to claim this is a incomplete metric space, which means we want to claim what? There is some Cauchy sequence in here which doesn't converge, right? Which is not convergent. What is an example of a Cauchy sequence in this metric space which is not convergent? You may have in your mind. I believe I have already used this example last year in the real analysis, I believe. So let's let f sub n of x. Now that's a sequence of functions in L sub C2, right? Which is defined by 0 if x is less than -1 and x plus 1 if x is between -1 and 0 and negative nx plus 1 if x is between 0 and 1 over n. And 0 if x is more than or equal to 1 over n. Yeah, that's our definition of the function f sub n. F sub n. For all natural number index n. Do you imagine how this function looks like? How the graph of that function looks like? That looks quite much complicated, but that's a piecewise linear function, kind of, right? Where the function value of f sub n is 0 to everything to the left side of -1. And the function value of f sub n is x plus 1 between -1 and 0. So between -1 and 0, we have this linear function that looks like this, right? And between 0 and 1 over n, the graph of function, the function value of f sub n is what? Another linear function, which is -nx plus 1. So that must be a decreasing straight line like this because its slope is -n, which is negative. And to the right side of 1 over n, the function values go back to what? Constant zeros. Yeah, that's about how the graph of the function f sub n looks like in the xy coordinate. You easily recognize this function f sub n is in L sub C2, right? Because this f sub n is what? Everywhere continuous, and that's square integrable. F sub n values are mostly 0 outside of that interval between -1 and 1 over n. So what? That's definitely square integrable. Riemann integrable. Its square is also integrable, right? So each f sub n is in L sub C2 for sure, right? And then what is our next step? Our next step is to justify that this f sub n sequence is a Cauchy sequence. Then how do we prove that's Cauchy? To prove its quotient, let's look at the difference between the two f sub n and f sub m, f sub n and f sub m. Let's look at the difference between the terms of that functions, f sub n and f sub m, right? You know. We want to claim, first of all, we want to claim the sequence f sub n is Cauchy in the subset L sub C2. How do we claim that? To claim the quotient of the sequence f sub n, let's look at the difference between f sub m and f sub n, right? So let's assume the first index m is more than the second index n. Then let's look at the distance between the corresponding terms of the sequence f sub m and f sub n, which is defined by, oh, sorry, I have missed half power on the definition of the metric between f and g. Yeah, we must have half power of integration of square of the difference. That's how we must define the distance between the two functions f and g. That was what I have missed. Yeah, half power must be there. Yeah. So then what happens to the d distance between the corresponding two functions? That's exactly the same as what? By the definition of the metric d, that's the half power of integration of square of difference between f sub n and f sub m. Then by the definition of f sub m and f sub n, what happens to their difference? F sub n is this graph here. So f sub m may be something like this here, right? Something like that, right? So what is the difference between f sub n and f sub m? The distance between f sub n and f sub m is what? Less than or equal to 1, right? Because the top point over here, is what? 0, 1. That's the peak point of all f sub n's. So what? And then, 1 over n is less than 1, so the difference between two functions f sub n and f sub m must be what? Less than or equal to 1. Their difference is n most 1, what I mean is. So the whole integration over here is, what am I doing here? The whole integration over here is what? Less than or equal to 1 square, which is 1. But we can restrict our integration domain here, right? Because outside of that interval, all the function values are 0, so then our integration range must be what? Restricted to from 0 to 1/2. From 0 to 1/2. Outside of that interval, we have identical function values of f sub n and f sub m. So outside the interval from 0 to 1 over n, their distance is what? Their distance must be 0, disappear. So what is the computation of this integration? This integration of that computation is 1 over n. What is the half power of 1 over n? That is exactly what? 1 over square root of n. So the d distance between the two functions f sub m and f sub n in the space there is what? Less than or equal to 1 over square root of n, but 1 over square root of n sequence converges to 0. So what must we conclude? we must conclude what? The sequence f sub n is a Cauchy sequence. So the distance between f sub m and f sub n converges to 0 if two indexes m and n approaches infinity. That was what we have claimed. So we must conclude the sequence f sub n, the sequence of functions, is a Cauchy sequence. In the subspace metric, that's a Cauchy sequence. That was what we have claimed. So f sub n sequence is a Cauchy sequence in the subspace metric. But we must claim this Cauchy sequence does not converge anything in the subspace metric, right? That's what we must, claim. First of all, let's justify that what? This Cauchy sequence converges to something in the large original metric space L2. We want to claim that what? This Cauchy sequence f sub n is not convergent in this subspace metric. That's what we want to claim. Before we claim that, let's claim that Cauchy sequence converges to something in the original large metric space L2. That's what we must. Let's justify that first. Then on the original matrix space L2, you already know where that sequence f sub n converges to. What happens as n goes to infinity? If n goes to infinity, then what? 1 over n is getting smaller and smaller and getting closer and closer to 0, right? So, as n goes to infinity, this function f sub n is getting closer and closer to this discontinuous function. Yeah, what happens as n goes to infinity? As n goes to infinity, 1 over n goes to 0, converges to 0, approaches 0, so what? This piece is disappeared as n goes to infinity. This piece is disappeared. As n goes to infinity, what? This piece is getting closer and closer to zeros, right? But the other piece over there is fixed by the same straight line. So as n goes to infinity, what? As n goes to infinity, the sequence f sub n converges to this discontinuous function g. Discontinuous function g. This is the graph of the function g. And as n goes to infinity, this sequence f sub n converges to this discontinuous function g pointwisely. Well, this discontinuous function g is in what? The original metric space L2, but not in this subspace metric because that's discontinuous. Yeah, this discontinuous function g is in where? The original metric space L2, but that's not in the subspace metric L sub C2. So we want to prove this sequence of functions f sub n converges to this function g in L2 first. That's what you want to claim on the next step. The next claim is that the sequence of functions f sub n converges to the function g on where the original metric space L2. That's what we want to claim here. Where is G located? G is not located in the subspace matrix. G is located where? In the original metric space L2, right? Because that's discontinuous. So that's not in L sub C2. That must be in L2, the larger original metric space. And we want to claim the sequence of functions f sub n converges to the function g on the original metric space L2. Which is easy. How do you claim that? For its convergence, let's look at the distance between f sub n and g on L2D metric. L2D metric. That's same as half power of integration of square of difference between f sub n and g. But that's less than or equal to 1/2 power of integration of what happens to the difference between f sub n and g again. What is the difference between f sub n and g? The difference between f sub n and g is what? N most 1 again, right? N most 1. F sub n looks like this, but g looks like that, right? So their difference is what? N most 1. Less than or equal to 1. Their difference is less than or equal to 1. 1 squared is 1. That's what's happened. But what is this integration interval? The integration interval is again what? From 0 to 1 over n. 0 to 1 over n. Outside the interval, both functions f sub n and g are disappeared. So what? Their difference is 0. So our integration interval is restricted to from 0 to 1 over n. So what is this computation? This computation of integration is again 1 over square root of n, which converges to 0 as n goes to infinity. So we have claimed the sequence f sub n converges to that discontinuous function g on the original metric space L2. That was what we have claimed. We have 5 more minutes, then I hope we could finish its proof on the next 5 minutes. First of all, we have proved that that sequence of functions f sub n is a Cauchy sequence in the subspace metric. That was the first claim. On the second, we have proved that the sequence of functions f sub n converges to some function g outside of L sub C2. That was what we have claimed secondly. And then, what is our last claim? Our last claim is that the sequence of functions f sub n does not converge to anything in that subspace using contradiction method. That's our last step. So we want to claim what? We want to claim that the sequence of functions f sub n does not converge to any f in the subspace metric. That's what we want to claim finally. F sub n is a Cauchy sequence in this subspace metric, but it is not convergent on the subspace metric. Then what? We concluded that what? The subspace metric is not a complete metric space. And how do we claim that what? That sequence of functions f sub n is not convergent in that subspace metric? We will use the contradiction. Suppose the sequence of functions f sub n converges to some f, for some f in the subspace metric. Then what contradiction do we derive? Then what contradiction do we derive? Then what happens to distance between f and the discontinuous function g we have defined there? By the triangle inequality that is less than or equal to, by the triangle inequality, this distance is less than or equal to distance between f and f sub n plus distance between f sub n and g. By the triangle inequality. By the triangle inequality. But what happens to both distances? We supposed f sub n converges to f, right? So this first distance converges to 0. And what happens between f sub n and g? We have already claimed what? F sub n converges to g in L2 distance. So this distance converges to 0 as well. So then what must we conclude? Distance between f and g is of course more than or equal to 0, but less than or equal to some sequence converging to 0. So by the squeeze theorem, what must we conclude? By the squeeze theorem, we must conclude what? Distance between two functions f and g must be what? 0. Equivalently what then? By the definition of the metric space, if the distance between two values is 0, then what? That's equivalently what? Two functions f and g must be identical. Is it correct? Is it correct? F is where? F is in L sub C2. But G is not. Am I right? Because G is not continuous. G is not in L sub C2, but F is in L sub C2 because what? F sub n converges to F in L sub C2, which we have assumed. So that's a contradiction. They cannot be equal to each other. That's a contradiction. Why do you have that contradiction? The reason why we have that contradiction is because what? We supposed the sequence of functions f sub n converges to f in the subspace metric. Right? That's the reason why we had derived this contradiction. So we must conclude what? This Cauchy sequence does not converge to any in the subspace metric. That's what we must conclude finally. So we conclude this Cauchy sequence in the subspace metric is not convergent in the same subspace metric. That's what we concluded. So we conclude what? That subspace metric with distance d is not a complete metric space. Period. Right? So that's a nice example of incomplete metric space we have. Because this subsequence is not convergent in that subspace metric. So not every Cauchy sequence converges in this subspace metric. So this subspace metric is not a complete metric space, unfortunately. So that's an example of incomplete metric space. Okay, yeah, let's continue next time.